Okay, our last result for this section is another result we promised. So suppose R is a PID and U in R is irreducible. Then U is prime. Proof. So again, prime always implies irreducible in a domain. We saw examples where irreducible elements were not prime. However, in a PID, they are. Proof. Well, suppose U is irreducible. We show that the ideal generated by U is a maximal ideal. To that end, suppose that U is contained in some other ideal, M, generated by M, contained in R. Okay? And we're allowed to specify here that the ideal is principal because the ideal in between is principal because we have a PID. Okay? So we're using PID at least once right here. Now what? Now let's use that U is irreducible. So we know, let's see if I can get my divisibility right this time. U is in the ideal generated by U, so that's contained in M. So U is in M, which means that U is a multiple of M for some K and R. Oops. Dang, messed that up. But U is irreducible, so either M or K is a unit. Hopefully this is looking a little bit familiar. If M is a unit, then the ideal generated by M is all of R. If K is a unit, then the ideal generated by M is the same as the ideal generated by U, as U and M are associates. And associates generate the same principal ideal. So whenever you have an ideal in between U and R, it must be either equal to U and or R. Or said differently, if I have the ideal generated by U and it's properly contained in some ideal, that ideal must be all of R. So the ideal generated by U is a maximal ideal. And so it's a prime. And so the element that, by the problem that I promised I would assign in the previous video, U is a prime element. If I generate an ideal which is prime, I must have used a prime element when I have a PID. Okay, cool. So in a PID, irreducibles and prime are the same thing. And so in particular, a consequence of this, suppose you wanted to take a field and look at polynomials over it, and you wanted to mod out by a polynomial, and you have some questions, namely, maybe a question you have is, do I get a field or a domain? By what we've done, it's all dependent on if P of X is prime. If it's prime, then we're modding out by a maximal ideal because we have a PID, so we get a field. But by the theorem we just proved, it's actually not all dependent on that, which is a harder definition to apply in this setting. It's actually dependent on an easier thing. It's all dependent on if P of X is irreducible. And so then this, a consequence of what we've done is that this actually leads us to a new question. What are tests for irreducibility? How can I tell if I'm unable to factor? Factoring is actually quite hard. Even just factoring, whole numbers is hard. So what are tests for irreducibility? And that's something that we're going to investigate in our last week of class.